Of course, drugs really are just state neurotransmitters, right? At their very essence, cocaine, inhalants, hashish are all simply neurotransmitter mimics. That's all they are. Right. But first, to wake you up, get your brain going, see how much you remember from last time, if anything. What ion reestablishes memory potential? So your action potential has swept by. You're positive 40 millivolts. We're going to go back down to minus 60. What neurotransmitter, what ion is going to reestablish minus 60? It was okay to cheat. Get off the notes from last time. I don't mind. Okay, do it a little fast. It's okay too. You can cheat on the clickers. You can't cheat on the test. Shall we start the clock? I don't see why not. Reestablish it by the opening of voltage-gated ion channels, letting which ion come inside. So the correct answer is potassium, right? The next most popular choice was chloride. Chloride is not involved in the resting membrane potential. It's involved in drugs like Valium, we'll talk about in a minute. It's not sodium because sodium establishes the action potential. It is not reestablishing. The sodium-potassium pump is not, I say again, the sodium-potassium pump is not the reason this process occurs. The sodium-potassium pump, which does kick sodium out and let potassium back in, is the slow bilge pump. It's cranking all the time at very low levels. It's just not fast enough. It needs some other mechanism, and that other mechanism is the opening of voltage-gated potassium channel. All right. Potassium ion sweeps in, that makes the cell, sweeps out. Let's talk about Don first. It's not my patient, but a good story. Retired accountant, got tremor, slowing movements. We're going to talk about Parkinson's disease when we get to the movement part of our course. He's got PD, Parkinson's. So he took some levodopa. What is levodopa, and how does that make dopamine levels go up? And we're going to come to that in a second. A couple of years later, motor symptoms began to fluctuate, and the dopamine receptor agonist, propinerol, was added. Dopamine receptor agonist. What do agonists do? They do. Can I ask a question in class? Did we finish the last lecture? Yes? All right. Just making sure that I was on the right part. I thought I was. It was brain free. Okay, good. Then he became a gambling addict. And the question is, why become a gambling addict? Well, people become addicted to gambling. Can you be addicted to gambling like you can be addicted to cocaine? Yep. It can be just as potent force. And he lost $100,000, which he may or may not have had to lose. I don't know how rich he was. But that's a big chunk of change, right, in a relatively short period of time. Every day. So went back to the neurologist, and they said, you know, maybe this propinerol was the problem. How can a drug cause me to be addicted to gambling? That's impossible. Isn't addiction a moral flaw in us? And how can drugs cause moral flaws at age 67? Are you too old to be this? But of course, what happened? His addiction went away. $100,000 in the hole, but better late than never, perhaps. So the question is, how could this happen? What's the link between drugs and addiction, between dopamine and Parkinson's disease, between dopamine and addiction? Gambling per se. All right. There are two receptor subtypes. This is the boring part. Ionotropic and metabotropic. Neurotransmitters are going to cross the synapse and bind to some receptor. And there are two big classes. And the two big classes have unwieldy, ugly names, but you'll be able to tell what they do and be able to predict what they do based on what you think a neuron should have to do, what its job is. Put yourself in the place of the great engineer. Great engineer. Ionotropic receptors. They cross the neurotransmitter crosses it, binds here, opens up an ion channel, chloride comes in, sodium comes in, calcium comes in. That's it. We've already discussed this already. So we've already done ionotropic receptors. We haven't given that name. Now we have. All we've done is add a name to a concept you already know. Piece of cake. That's fast. It's reliable. Simple. It's not very fancy. In contrast, these guys over here, the metabotropic parts. Metabotropic. Metab means metabolism. Well, is metabolism easy or hard? Complicated or simple? That's an easy question. Metabolism is incredibly complex. Millions of pathways, millions of steps. And so metabotropic receptors are very complex, not like the ionotropic guys, which are just ion channels, pure and simple. So metabotropic receptors, very complex. It's kind of the analogy of talking about neurons. Neurons can be unipolar or multipolar. Multipolar neurons are complex. They have room for lots and lots of input, up to 100,000 cells can input on one single neuron. It's the same concept. Metabotropic receptors have lots of inputs, lots of steps, lots of ways to tweak it. If you're a drug company working on some receptor, do you hope for your company that it's ionotropic or metabotropic? You hope it's metabotropic. And the reason for that is that if metabotropic, lots of steps. That means many places I can invent a drug to act and therefore patent that drug and make a fortune, which is drug companies are designed to do, right? That's the name of the game. You've only got one step. That one step, someone else may have already done it. There's no place for me to make any money. And fortunately, you're going to guess already that most receptors in the brain are metabotropic. It's also complex. Right. So there are two types. Another way to say what I just said, same information, different way to put it. Ionotropic receptors are direct. They're simple. They're fast. They're active. Incredibly reliable. Neurotransmitter binds. It opens up this ion channel. The blue ions come inside the cell and whatnot. So they are ligand gated. What are ligands? Anything that binds to a receptor. What are ligands? Neurotransmitter, cocaine, alcohol, whatever. In contrast, metabotropic guys are indirect. In fact, here's the ion channel to the right here. This is not where the drug binds. It doesn't even bind it. It binds next door. Next door. Well, what's next door? Some other place. The metabotropic receptor. Well, there's got to be a link between these two, right? Otherwise, one would not affect the other. And there is. And where's that link? Right down here. So it's a multi-step process. And multi-step processes are the bane of your existence, right? Because lots of stuff to memorize. But for our class, we're not going to memorize all the pathway, all the steps of G proteins, thank goodness. The idea receptor, the neurotransmitter binds to this receptor, causes this blue molecule, a G protein in our case, to physically detach, go over here, bind the ion channel, and then open it up. So the same thing happens. We both open up ion channels in the top and the bottom panel. It's just we do one directly, ionotropic, and one indirectly, metabotropic. That's the concept. Is that clear? Simple? You need not memorize this unless you're really bored. Unless you're going into be a neuroscience major, then you might need to. But for now, not necessary. Just to give you a flavor, of course, it's a simplified version. There are many more steps this diagram does not even show. But that's okay. Here's the ion channel in green. Here we're going to bind the drug or neurotransmitter here. Causes some changes to occur, a cycle. It ultimately has the properties of opening or closing the ion channel. Right? The drug companies can invent a drug that walks step number 1, number 2, number 3, number 4, 5, 6, 7, and then some. All right. So in Don's case, we talked about a drug being a dopamine agonist. What does that mean? If you're an agonist, does that mean that you don't believe in God? That's a different thing. Does it mean you're in pain? You're in agony? No, not quite. An agonist is simply a drug or molecule of any kind that mimics the natural receptor. What that receptor usually does, an agonist, is a molecule that also does that. It's a mimic. So agonist equals mimic. Put those two down, you'll be in good shape. Agonist means mimic. So here's an example. Here's our channel in red. And the hormone, neurotransmitter, are going to bind to this. Let's say it's acetylcholine. It binds here, opens up the channel. Ions come inside. Very simple. But now we've invented a drug. Here's our drug. It looks kind of like this drug, the natural ligand, but it's a little bit different because it's not the same chemical. It's missing a methyl group. It's got an exosulfhydryl group. It's been tweaked in some version. And so it binds to the receptor. Here's it. It tries to fit in this nice square shape. Well, it's not exactly square shape, right? Because it's a different protein, different molecule. It fits pretty good, and it kind of turns on the cell a little bit. Some molecules fit perfectly, not very many, but some are perfect mimics. They look identical twins, so to speak. Not the same, but they look the same, and they can act the same. Most drugs are partial agonists. Well, we don't get the full bang for our buck, as we do with the natural one. We get half one. It's a half partial agonist. It's similar to, but not identical to, the natural ligand. It's an agonist, but it's a mimic. That process is very simple. A dopamine agonist, therefore, propranolol, is going to do what to dopamine activity? It's going to mimic dopamine activity or block dopamine activity. It's going to mimic it. So a propranolol is a dopamine agonist. It's going to act like dopamine. You might say, well, why not just give the patient dopamine? Won't have dopamine, just give them dopamine. Why do you have to give them a drug that's similar to, but not the same as? Okay, so one possibility, the brain will react to the presence of dopamine. And that's true, but pharmacologically the reason is dopamine doesn't cross the gut. You can't get dopamine to the brain. You can't give dopamine. The brain will never see it. So you give something that's like dopamine. All right. So that's agonist. Antagonist, anti-agonists are just the opposite. So if you got one concept, you already got the other concept. Here's the natural ligand up here. Here's the red. It's going to bind here. It's going to do its thing just as always. It's our natural situation, what the body is designed to be. But now you've invented a blue drug. And the blue drug is going to fight. It's going to bind to that receptor site. But when it binds, it doesn't do anything. You have a lousy key or a key that doesn't quite fit the lock. A key that's not meant to be for that lock, but it's kind of similar. Like you're in a dormitory. All the keys look kind of the same, right? But they're slightly different. But if you put your key in your across the hall room, it's not yours. The key goes in, but does the lock turn? Nope. It'll go in halfway, entirely even, but it won't turn the lock. But while your key's in there, can your neighbors get in their room? You put your key in there and glue it in because you don't like them. You find a key on the ground, you put glue in it, so can they get in? They can't because the receptor is blocked. The key is blocked. Keyhole is blocked. That's what we're talking about. So if you bind here, nothing happens, but the real guy can't bind. The real guy in red and gold is the natural ligand. And once you're occupying that receptor site, once you're sitting in that parking space, can't nobody park there. It's competitive because it's a competition between you and the natural ligand. First one there wins, right? First one there wins. So when you came this morning, so you drove a car. You got here about 9:45. Parking spots are scarce. The green lots probably are gone by then. And you found one spot. You zoom there to get that spot, right? Because the other car coming this way is trying to park there too. And the first one gets there, wins. First come, first serve. It's a competition between you and another ligand. Only when you bind there, nothing happens. Because you're not supposed to be there. Competition. Is that clear? Because that's the easy one. The hard one is the one below it. Non-competitive. Well, how can you be non-competitive? Well, it's sneaky. Non-competitive antagonism is underhanded, sneaky, tricky. Let's say, for example, that you and Dr. Daniels have had a fight. Dr. Daniels runs his place, in case you don't know who he is. He's the president. And so you're mad at him for some reason. Whether it's justified or not, I won't go into. Maybe it is, maybe it's not. But you know where he parks. I know where he parks too. Parks over near the AD building. And you could, of course, come in the morning and park in his parking spot. And therefore, when he comes at 8 o'clock, he can't get there. Right? That is competitive antagonism. If you're in his spot, he can't park there. Of course, the problem is they tow your car. So it will not be a permanent inhibition. But what else could you do? What else could you do? Do what? You could block him from leaving. then he has to stay at work and do you more damage. You want him to go home and stay away. What if you park right next to his parking spot, in a legal spot? It's not his spot, but right next door, before he gets there. Well, how does that do? Well, before you leave your car, you turn up your multi 10,000 watt stereo, and so your car is bouncing up and down like this, shaking the windows, you're rattling. And so when he pulls in to park at his spot right next to your boombox car, his car starts shaking, and he says, I can't park here. I'm going to destroy my car. And so he has to go somewhere else. Pretty sneaky, right? Underhanded. You park legally, but you prevented him from binding to his parking spot. That's non-competitive. Well, it's competitive on a indirect kind of measure. So that's the idea. You're going to park, not the park. Here's a parking spot. Here's a receptor site. You don't park there. You park right next door to the triangular-shaped receptor. But your binding there prevents the natural ligand from binding, or binding properly, or binding for long enough. You can treat it various ways. Non-competitive antagonism. Okay. Of these two choices, which one do you think the brain does most often? That's correct. How did you know it's non-competitive antagonism? Because you got a class in pharmacology already? Maybe. Did you follow general rule? What? The brain does it the most complicated way possible. Given a choice, the brain always chooses the most complex way. Why? I thought the brain was about efficiency. The brain's about control. And the greater the step, the more pathways you have, the more possibilities, the greater the control the brain can exert. So the question is about non-competitive antagonism. Remember the parking lot example? You'll be golden. Did it make sense? Maybe it didn't make any sense to you. Okay. We're focusing on this part of the neuron, the axon terminal, where the neurotransmitters live. Are they going to migrate down? The vesicle membrane melds with, fuses with the presynaptic membrane. The molecules drift off, cross the synapse, and bind to the postsynaptic receptors. Some competitive antagonism, some non-competitive antagonism, some agonists. So some are going to support ion channel function, others are going to block ion channel function. It all depends on the particular molecule. And drug companies love this slide because this is where they make their money. This slide is why neuropharmaceutical companies are in business, because they're inventing drugs to block or improve each one of these processes. So every drug, almost every drug that we have for the brain, for the nervous system, interacts with one of these steps here. One of these steps here. And I think for this class, I don't think you have to memorize this slide. You don't require that. But at least get a flavor of all the many steps that you can do. All right, neurotransmitters. This you got to know, because this is the basis for the rest of the semester. So memorize the next slide. 1, 2, 3, 4, 5 classes. We could actually make a few more if we wanted to. We have. This is a nice old-fashioned slide. Way to start, I think. Neurotransmitters can be defined by their chemistry. I hate that word, right? Don't you hate the word chemistry? Amino acids, monoamines, something called soluble gases. That sounds insane. Acetylcholine has its very own class. We've already done that one. And things called neuropeptides. We're going to go through this one by one by one. Keep in mind, as we do this, how this affects your brain, your child's brain, your brother's brain, to make it more real. Amino acids, glutamate, aspartate, glycine, and GABA. Those 4. Should I remember all 4 of those? You sure you should? Do you have a mnemonic for me? Sure. Amino acids make me gag. Right? Highly useful. You probably already memorized it now. Glutamate, aspartate, glycine, GABA, they make me gag. I'm going to go those 3 of those 4. We're not going to do aspartate because we'll come back to it a little bit later in the semester. But we're going to do glutamate because glutamate is the single most important neurotransmitter in your brain. So if I had to pick one most important neurotransmitter in human brain, it's glutamate. In other species, not true. But in humans, which all we care about is glutamate. It's the most common excitatory neurotransmitter. That's a great test question, right? You recognize that as a really good test question? in brain and spinal cord. And glutamate, here's a molecule, a neurotransmitter, on the postsynaptic membrane combined to glutamate receptors. Well, glutamate receptors have 3 subtypes. There are 3 kinds of glutamate receptors that are ionotropic. That word again, ionotropic, what does that mean? If glutamate binds to the AMPA receptor, right here, glutamate binds to AMPA, what's going to happen? Is that going to simply open it up and let ions flow in? Or is it going to set into motion a cascade inside the cell mediated by G proteins? Which one is this? This is the active, simple, direct. It's just going to open up the channel, ions are going to flow in. The simple version. I mean, there's 3 receptors for it, depending on how glutamate binds. The receptors can be slightly different in their chemistry, and we don't care about the differences between these 3 at this point. We will care a great deal about it later when we talk about learning. How your brain learns stuff. It's this distinction that's important. Ionotropic, AMPA, NMDA, and kainate. Is it not? Agonists. Glutamate has 3 kinds of ionotropic receptors. It's also got, in addition, it's got 1 or 2, several, but we're talking about 1 kind of metallotropic receptor. You mean glutamate goes both ways? It does. It's a bimolecule, goes both ways. Ionotropic and metallotropic. Because it's the single most important neurotransmitter in the brain. It's going to do things as complicated as it possibly can. It's going to have both classes. You said, I've seen this kind of picture before. We got glutamate, binds here. G protein stuff happens inside the cell, and here's the ion channel that's going to open up. Same idea as before. Stop at this patient. Here's his Trey. This is one of the saddest stories you'll ever hear. Trey is a 5-year-old boy who was walking across the parking lot of his East Dallas apartment complex about 5:15 or so one afternoon. And a car came around the bend. The car was going, the witnesses say, maybe 5 miles an hour. It was not speeding to the parking lot. Everybody agreed with that. In fact, what actually happened is Trey walked into the car. Okay? Because 5-year-old boys sometimes are not when they're going. And the car was going slowly, and Trey just was running, I think, and just ran into the car. Hit the side and bounced off, of course, and fell down and bumped his head. Started crying immediately. The car stopped. Every mother in the park complex appears on the balcony. Right? The mother whose child Trey was hears his voice, goes down, picks him up. He stops crying. She takes him up to the apartment. Right? You're going to be okay, dear. Had a goose egg on his head. And the neighbors all came around and said, you should take him to the hospital. He got hit in the head. He could have a concussion. So she said, maybe you're right. He looks okay to me, but still you may be right. So she takes him to a local hospital, downtown, Dallas Hospital for children. Forgot the name of it. All right. And it's in the emergency room about 5:45 or so, where he was talking, knew who he was, but a little bit sleepy. So he said, we'll watch him in the ER for a while. A few hours later, 2.5 hours later or so, he was no longer really recognizing Mom, stopped talking, said, well, this is worrisome, let's admit him to the hospital for observation. So got admitted, and around midnight, so 5 p.m. or so was the injury. Around midnight, the nurse on the floor said, he's unarousable. You cannot wake him up. We transferred to the ICU on the way from hospital bed to the ICU. He went down to radiology and had a CT scan. So I can read CT scans now. I'm an expert at this. I know this is a radiation test, and the scan is abnormal. What's wrong with the scan? Why is it abnormal? Inflammation. The brain's inflamed. Specifically, the brain has got too much water in it. The water content of the brain is much more than normal. It's called cerebral edema. Remember we discussed cerebral edema before a few slides back, a few lectures back? I showed you a pulsating brain. And I told you that brain begins to swell, an ailment not to be treated, according to the Egyptian physicians. And I told you it hadn't got much better in our century. Here's the goose egg on his head. Here's the bump where he fell back, hit the back of his head. No big deal. It confirmed he had trauma. And at 8 p.m. the next day, at 8 o'clock the next morning, he's dead. He died. despite ICU care and all the things that medicine can do. And the question is, should be in your mind, mother's mind was, what happened? I brought my child to you, he bonked his head, and he was dead the next morning. The supposition would be, our mother, that somehow you did something wrong. You somehow led to the death of my child, because children fall down all the time. 5-year-olds fall down every few minutes and bonk their head all the time, and yet my child died for that. What happened? Trey exemplifies excitotoxicity in a very dramatic way. A reaction of nerves in the brain to mild trauma, as best we can tell, mild trauma. And it caused too much glutamate entry to the cell. So glutamate came in the cell exuberantly, more than it should have. The glutamate channels were wide open. Glutamate is not coming in the cell. Glutamate is binding to the receptors and opening the channels. And sodium and calcium are coming inside the cell. And that entry brings in water, and the brain fills up with water as you see on the scan. The brain swelled, brain pressure went up, it compressed his brainstem, he could not breathe, and he died. Stopped his heart. Is that clear? Yes. So the question is, if he come in earlier, could have been saved. He came in less than an hour after the accident. And of course, what was done for him in the hospital? The first 8 hours? Nothing. So coming earlier would make no difference at all. So the question is, can we drain the fluid? The fluid is inside the neuron. And we can't drain fluid out of neurons very effectively. We tried, and obviously failed. Yes. Yes, he had treatment. The treatment, as you can tell, is ineffective. Had we started treatment when he first came in the door, it would have made no difference. So his question is, why Trey and not every other 5-year-old that you know? Why Troy Aikman? Why did Troy have to quit football when his peers, Randall Cunningham, could play for decades after that? Why did Troy have to quit? You're Cowboys fans, right? Or some of you anyway. Troy Aikman used to play quarterback for the Cowboys, who were a football team in Arlington. He was great, but he retired early because concussion. He had repeated concussions. When he retired, he told the media in his retirement speech that he had at least 10 concussions. I know the neurologist who takes care of the Cowboys and said Troy's had at least 20, at least, because nobody really has a count. So what is about Troy's brain that makes him like Trey? And that's what many places around the country are trying to figure out. The NFL is giving $750 million to try to figure this out. Why some football players and not other football players? And is it genetic? It probably is. So I think you're right. So glutamate can be good, can be bad. Too much excitation can be deadly. And one slide summary of glutamate. It's got on the left here. On the left here. Ionotropic receptors. 1, 2, 3, AMPA, NMDA, kainate, and its glutamate receptor in red. So far, so good? Pause for questions. All right. Amino acids make me gag. We're going to skip aspartate, so we can go from glutamate to GABA. The most common inhibitory neurotransmitter in the brain. Glutamate and GABA. And most start with G's. I'll get them mixed up. Most common inhibitory neurotransmitter in the brain. Inhibitory. How can the nerve cells be inhibitory? I know. We can let which ion come inside the cell? One that's negatively charged. That one. That one is called chloride. That's how it all works. We can open up channels for chloride. Chloride is masked outside the neuron. The channels open up. It rushes inside the cell. Ionotropic receptors. Very fast, very lively. But look close at this particular channel. So here's where GABA binds. But this receptor's got places for other folks to bind to. People that you know, people you're familiar with. People like alcohol. Alcohol binds here. How about barbiturates? They bind here. How about Valium? It binds here. Ativan, lorazepam. And steroids bind here. So this receptor has got a lot of places for it to bind besides GABA. GABA is what the brain makes, but the pharmaceutical companies and nature have made other things too, right? Nature's made ethanol. We can now do it too. The drug companies have made benzodiazepines. And you might say, you know, I don't get why evolution was prepared for the 20th century pharmaceutical companies to make Valium. It's been preparing for millennia, having a receptor site ready to go so that when we invented Valium, it's got a place for it to bind. Shouldn't that be surprising? I mean, drug companies are powerful, but can they control evolution? I don't know, maybe they can. Maybe they can. Opens chloride channels. It's inhibitory. It's going to cause the cell to be depolarized or hyperpolarized. Depolarized or hyperpolarized. Everybody thinks it's hyperpolarized, should raise a hand. Good job. We'll talk about these drugs when we talk about depression, anxiety, mania. We're going to be trying to slow down the nervous system. We want to block the nervous system. How about the treatment of seizures? I showed you movies of seizures last time. Kids jerking, adults convulsing in the bed. If a seizure goes on and you want to use a drug to stop the seizure, as we often need to, what kind of drug would we give? Would this work? It's going to nervous system seizure is it's too much firing of neurons. If we give a benzodiazepine, would that work? It will. And so this is the drug of choice to stop a long seizure. The drug of choice. Benzodiazepines. Glycine, the last amino acid. It's in red, right? It's in the spinal cord. Glycine is really a spinal cord only neurotransmitter. Isn't it? Kind of like tetanus. Remember tetanus? Anybody remember Sheila? Probably not. The lady went like this because she got tetanus, and the tetanus made tetanus spasm, which bound to glycine receptors. And what happened to her? She became like this. So tetanus spasm blocks, irreversibly blocks glycine receptors. That's an antagonist or an agonist. Irreversibly blocks the receptor. Antagonist. So tetanus spasm is an antagonist for glycine. Blocks glycine. Glycine is inhibitory. By block inhibition, what does the patient do? Does she become paralyzed? Or is she rigid, every muscle that contracts? That's why she would arch like a pretzel. What else could I use? Strychnine. Where can you get some strychnine if you need some? At a feed and seed store, one on Maple Avenue, for example. Why is strychnine used in the, why they sell strychnine at the feed and seed store? To kill something, right? Rats? Anybody else? Cheating spouses? Is strychnine widely used in rural areas to commit murder? You bet. All right, West Texas, for example. Okay. So what happens? We take some strychnine. Here's what happens. You say, this sounds kind of like tetanus spasm because it's the same receptor. They both block strychnine. They both block glycine. And they become exquisitely sensitive to startle. So if you just make a loud noise or tap on the nose, they spasm. Very characteristic. And the death is caused, of course, by suffocation. Treatment is to put them on the ventilator, let the strychnine wear off, eventually they'll be okay, if you get to them in time. So it's not often fatal in current medicine if you can treat them in time. Practice. Which one is not? mnemonic should help you through this in no time. Everybody should get this right. What does A and GAG stand for? Aspartame. We're going to talk about it. That's what the A stands for. So dopamine does not start with G8 or GG. So it's not. This is the correct answer, of course. All right. A harder question, right? Because this requires figuring out what these terms mean. So, a second think about it. You're a drug company, you invent a new anti-smoking drug that's going to make billions of dollars every year, billions of dollars. It binds to nicotine receptors and stimulates them. It's going to be a partial agonist. You know, if you vote and change your answer, we take the last chance you pick. So keep picking that right answer until you're happy with it. All right, it is an agonist, a partial agonist. It stimulates receptors. It does the natural thing. It is not an antagonist. It could be inotropic, it could be metabotropic. I haven't got that far yet. So we don't know about those yet. But if you wanted to pick inotropic, that would be okay. All right. That's all amino acids. Don't forget about thread. The monoamines. Most of what people care about, I think, in behavioral neuroscience classes, is this category right here. Because people have a greater interest in dopamine and serotonin than they do in amino acids. Even though they're not as common, not as prevalent in the brain. But they do important things. There are two categories of monoamines, the catechol and the indoles. Catecholamines, indolamines. How to remember this? Easy. I think it's easy. These molecules end in what? Ene, and ene. Serotonin should be what it's called. That's enough for government work. And serotonin is the only indolamine. So if you memorize that serotonin is the only indolamine, then the other three must be the other category, whatever it is, the catecholamines. Dopamine, norepinephrine, and epinephrine. And it turns out that these guys, dopamine, norepinephrine, and epinephrine, are in that category for a reason, because they're sequels. They're a sequel as a movie. So evolution devised this first neurotransmitter called dopamine. And tried it out. Did it work out? Was it a hit? Did it make money? The answer is yes. It made a lot of money. Very successful in evolutionary terms. Lots of reproductive fitness. So let's make a sequel to it. Let's just take this molecule, we'll tweak it, and we'll get norepinephrine. Try that out for a while. That worked out okay? That was a hit. Let's do it again. Another hit. Epinephrine. Well, epinephrine was a hit partially. It was a big hit in some parts of the country. It bombed elsewhere. It was a hit in the peripheral nervous system. Epinephrine was a hit in the peripheral nervous system. It is not a hit in the brain. Therefore, you don't have adrenaline in your brain. Epinephrine and adrenaline are the same molecule. English name, American name. So finally, evolution gave up. Like a dead end street, seems like. And back in a million years, I bet we don't have anything more out on this pathway. Maybe we do. We seem to reach a dead end with the sequels. But these molecules, dopamine, norepinephrine, they were big hits in the brain, and one's made from the other. So consider this, these are twins we saw from London. Memory retardation, very bad seizures, severe developmental delay, and they had some biochemical tests that showed they had low activity of tyrosine hydroxylase. And on this graph, can you find tyrosine hydroxylase? It's hard. It's up here at the very top, and its job is to turn tyrosine into the first step of making dopamine, norepinephrine, epinephrine. So because they couldn't get started, they could not make any dopamine or any norepinephrine. They had a genetic defect in this molecule called tyrosine hydroxylase, the first patient ever described this defect. And they came to us for treatment. So what can we do? Well, we can try. We can't make dopamine. Maybe we'll give you some dopamine. The problem is he just asked, how do we get dopamine? You can't eat dopamine. You can't take a pill because the gut destroys it. Well, what can I do? How can you give dopamine? You can give dopamine directly into the brain. What? So he's just taking the precursor. The precursor acts on what? So the precursors were tried, they were ineffective. You said dopamine helped? Remember Don the accountant? What drug was he taking? You can give epinephrine, it doesn't cross the blood-brain barrier. And the brain is what's the chief problem. So if you remember Don the accountant, he was given, the first drug he took was a drug called L-Dopa. It's the second box right here. And Dopa was turned, you can't take dopamine. But his suggestion, why don't we just take the precursor? Okay, so people with Parkinson's disease who can't make dopamine, we give them the precursor, DOPA, L-Dopa. And the brain turns that into dopamine. So that'll work. We give them the precursor. That is still the mainstay treatment for Parkinson's disease in the United States and the world. Those three memorize. Epinephrine in the periphery, not in the brain. It's made in a particular part of the brain. Think about evolution again. This helps me memorize things. It may not be entirely true. I don't really care if it's true. Why I can remember it better. Here's dopamine. Made in these cell bodies right here. So the site of production in the cell bodies, where all the DNA is, can make molecules like dopamine, lives in the bottom part of the brain, called the brain stem. It's the top part of the brain stem. This is the midbrain. Here's the pons, and here's the medulla. The midbrain, pons, and the medulla. We're going to talk about what we're talking about. It's in the midbrain, midway between spinal cord and brain. It's the name midbrain. And look where dopamine is. Look closely where it is. It's in the very front. Is that ventral or dorsal? Ventral. It is ventral. We're going to be talking about this place all semester long. The ventral part of the midbrain. Think about it in evolutionary terms. It got here first. They're the first students arrive in the class. They can sit wherever they want, and they're good students. They could sit in the front row, or they sit in the back row. They got here first. They want to make an A. They want to be successful. They want this to be a hit. They sit in the very front row. Imagine where norepinephrine is going to be. Can you already tell what's going to be? Is that the next one to arrive in evolution? We make dopamine. From dopamine, we make norepinephrine. Where's norepinephrine going to be? If you had to guess. In the back. I mean the back. It's going to be right here. Isn't that cool? The ventral brainstem. And dopamine goes two places. Two general places. One is, it goes from here, made in the cell bodies, transmitted down the axon. This is the axon here. Axon goes here. One neuron goes here. Another goes here. Sure, throughout the brain. So dopamine can affect the brain widely, diffusely. And affect concentration, mood, anxiety, ecstasy, orgasm, important things in your life, perhaps. All right. That's part of one. But another group goes right here, right? See these guys going halfway? They just go to part of the brain called the basal ganglia. The basal ganglia. That's the part involved in controlling your movements. Remember Don? He had what movement disorder? Parkinson's disease. So he got dopamine cells were dying. They projected right here. The neurons that projected here were dying. He took a dopamine agonist, L-Dopa, and the phenylpyranol to try to stimulate this. And it did. His Parkinson's gotten better. What else happened? The same drug that stimulated the dying neurons here also stimulated this pathway. And this pathway goes to things like The main reasons observing things like orgasm, sex, addiction, gambling. That's why Don became addicted to gambling. In a very simple term. Yes?
Don's medication was changed.
The ropinol was more effective for one pathway than the other. Because ropinol is a partial agonist, so it acts differently than the L-dopa does. It stimulates some dopamine receptors and not others. Put it that way. So here's norepinephrine, and you were right. It is maintained right behind it. This is the dorsal midbrain, and even down into the pons. It got here second, couldn't sit in the front row, so it sits in the back row. It kind of has to spread out. And a part of the brain called the locus ceruleus, and you should know the name of the locus ceruleus because it's the site of synthesis of the neurotransmitter norepinephrine, involved in things like mood, arousal, sexual behavior, part of our class. Mood control. Mood control. Some people talk about serotonin and norepinephrine in a very simple way. That's good enough for us. That it sets the idle speed for your emotions. Idle speed. What's idle speed mean? It's nothing going on. You're in peaceful. You're sitting around not under any undue influence of stress or drugs. And you have an idle speed. Your emotions are on an even keel. And that's the job of norepinephrine and serotonin. Dopamine has a different kind of job. Its job is to tweak that emotion, to give you the surges. Surges of things like ecstasy, like orgasm. Which one do you think might be related to addiction? Dopamine or norepinephrine? That's correct. All right. Is this a catecholamine? Serotonin, is that a catecholamine? Nope. It's an indolamine. Is serotonin a monoamine? Yes. G is okay. Get a cheat now. Well, we got here very last. They got here right when class was started. So where can they sit? There's 10 of them. This classroom is just about full. There's not 10 seats together anywhere that I can see. So if you come here right now, you got to spread out. And so they spread out. They're from top to bottom, front to back, dispersed throughout the entire brainstem. They're the serotonin. Last guys to arrive. But involved in similar kind of things that norepinephrine is involved. So serotonin and norepinephrine are very similar pharmacologically. Their distribution is more down here and less up here a little bit, but not a lot. We'll spend a lot of time talking in class about serotonin and talk about mood control. Questions so far? I know it's kind of boring. It's a lot of things to memorize, but it's a basis for every lecture from now to the end of the semester. So this is the part you got to have to do some blunt force memorization so we can use this information. So pause for not that important. Soluble gases, in the first place, are bizarre. This can't be true. I just can't believe that carbon monoxide is a neurotransmitter. I mean, carbon monoxide kills people. It's a gas. And gases, as you perhaps know, cannot be stored in vesicles because they're gas laws. They just float right through. Little tiny, they're only about this big, right? Little tiny things, they float right through the membrane. They can't store the stuff. So clearly these guys cannot be a neurotransmitter, but they are. They are neurotransmitters. As bizarre as that sounds. And this is nitric oxide, not nitrous oxide. This is not laughing gas. It's its chemical cousin. You can't store it. Therefore, when you make some, it's automatically released because you can't store it. And it's made right here, for example. Where's it going to go? If you make some here, where's it going to go? Everywhere. You mean it's going to affect this cell, and this cell, and this cell over here, and this cell up here? It's going to affect everybody in the neighborhood. So what is the point of such a bizarre system? Why would you want to have a neurotransmitter that floats affects everybody in the neighborhood? Think about your uncle sends you $1,000 and you decide to throw a beer party for your dorm. Gosh, you got the money and you want to spend it on your friends in the semester celebration. So you send out, you want to invite people in your dormitory to the beer party, but you don't want to invite the entire campus, right? You don't know these people. So what do? Could you get a megaphone, a loudspeaker, and say, in your dorm room, say, okay, everybody, the beer is here. Free beer for everyone. And so the folks Everybody in your dormitory will hear that announcement, but the folks across the street, across campus, are not going to hear it. You're just going to alert everybody in your dormitory. So what does that do? It synchronizes the activity of people around you. It synchronizes the activity. It lets them fire together. Last time we talked about the influence of being able to respond as a unit, a big group of folks. A bunch of neurons firing together have impact. Little neurons firing independently have very little impact. This is a way to get everybody on the same page, act at the same time. Is that clear? It's a way for me to know what you're doing. If I fire a lot, excrete a lot of nitric oxide, I may be 2 neurons away that I can keep tabs on what you're doing. A way for cells to communicate in a local environment, in other words. It's called a retrograde neurotransmitter because it diffuses out and affects everything. Retrograde, back against the grain, back from which most neurotransmitters are coming. That's the name for it. Can you buy some of this stuff? Sure you can. Does it work? Of course not. But it's your money. As far as I know, it's not harmful, so it's just a waste of money. But your results may vary. Make sure you keep that in mind. It's what? Nitric oxide. We're going to talk about the brain on it. We've already done acetylcholine in this introduction last time. Here's again. Its own classification. It is the very first neurotransmitter. The first neurotransmitter. All by itself. All by itself. There are many subtypes of glutamate receptors. Thank goodness there are only 2 main types of acetylcholine receptors. But both are important. Both are important for our test, for life, for treatment of disorders. And they're called nicotinic and muscarinic. Those names are bizarre, and they come from the kind of molecules that bind to them. Nicotine, you've heard about. Nicotine, made in the environment, made by plants. Humans can ingest it. And the plant, that molecule made by tobacco plants, for example, that nicotine can bind to this receptor right here. It does not affect this receptor. But another plant in the environment, you might guess which plant it is, right? Muscarine can bind to this receptor. So they're independent receptor types, and they're different. They have different purposes, different qualities. You should know about these 2 antagonists. So if nicotine is an agonist for this acetylcholine receptor, both these guys occur in nature. So does curare. It's curare. Curare is available in plants in South America. We discussed that briefly last time. Curare is going to be an antagonist. It's going to block this nicotine receptor. Therefore, when acetylcholine binds to it, it can't bind to it. This channel cannot be opened, and if you're a muscle cell, you cannot respond. Acetylcholine is being released, but curare is there. Curare is blocking the keyhole, blocking the pathway, blocking the receptor, and the result is paralysis. Acetylcholine is trying to bind to the muscle, because the muscle is this membrane right here. If you took a muscarine antagonist, would that person have paralysis? And the answer is no, because muscle cells don't make muscarine receptors. Okay, well, who makes them? The brain makes them. So, if you paralyze somebody with curare, do they become unconscious? They're paralyzed because you're shutting down these receptors. Do they also shut down brain waves? And the answer is no. And you tell me why. Why doesn't curare, which makes you paralyzed, shut down acetylcholine receptors in the brain? What? Because in the brain, there aren't any of these receptors to speak of. The brain is mostly muscarinic, and so curare does not affect it. If you've been to an eye doctor before, you've had atropine injected in your eye, probably. That's why they use to dilate your eyes. They use atropine or its chemical cousins. They block muscarine, and does your eye have muscarine receptors? It must, because it dilates your pupil. Same thing, nervous slide, same kind of information. Nicotinic receptors are inotropic. That word again. That means that they're fast and reliable. So when you smoke a cigarette, every time you get a bounce, every single time, not occasion. And it's very predictable, the bang you get from a cigarette. Highly predictable. It's excitatory. Nicotine is excitatory. Curare blocks it, and nicotine is the agonist for acetylcholine. In the peripheral body, in the muscle in the body, but not really in the brain, with one important exception. In contrast, the muscarinic guys are metabotropic. Brain things, take that complicated pathway, metabotropic. That means they can be excitatory or inhibitory, depending on how you tweak this pathway. So muscarinic receptors in the brain are complex, as you predict. In the periphery, simple, inotropic receptors that nicotine binds to. So if you ever smoke too many cigarettes, or your first cigarette, you develop twitches. Right? Too much nicotine makes you twitch. Too much caffeine makes you twitch. The same kind of thing. You can take a patch. Why would anybody take scopolamine? What is this over-the-counter drug used for? No one's ever taken a scopolamine patch? How come? This is for motion sickness, for seasickness. Does that make you drowsy? If you don't know, you haven't taken it. If you take a scopolamine patch, it says in the small print, don't drive cars, because it makes you drowsy. How about nicotine? Does that make you drowsy? Nope. Does curare make you drowsy? Nope. Doesn't affect the brain. All right. In the brain, the pathways for acetylcholine are similar to, but not the same. All the good spots in the brain stem were taken, right? So we had to set up shop in a different place. We're in the bottom part of the cortex, called the basal forebrain. The bottom part of the cortex, basal forebrain. And acetylcholine projects to cortex to cortex. It's not really projecting to things in the deep part of the limbic system. The limbic system is the site of emotions. Anger, fear, lust, sex, addiction, cocaine exposure, gambling. That is not acetylcholine. So the drugs that affect acetylcholine do not affect those pathways. Acetylcholine goes to part of the brain involved in memory, thinking, planning. What very common disease, getting more common by the year in our country, that we'll talk about in detail later, affects the brain when you lose these neurons. Alzheimer's. Alzheimer's disease is caused by loss of these neurons right here. Initially, by the whole brain dies. At the beginning of Alzheimer's disease, these cells begin to die first. But in Alzheimer's disease, it affects memory first, not emotions, not addictive behaviors. That's more products of the guys down here in the brainstem, which were dopamine, norepinephrine, and serotonin. We're almost done, right? Thank goodness. Almost done. The neuropeptides. Now look at this picture of the endorphins. There are many kinds of neuropeptides. Little bitty tiny molecules, little peptides, little bitty things. And the importance for us is this category right here, the endogenous opiates. So what does that mean? Endogenous. Endogenous means it comes from the body. It means the body makes its own. So I thought opiates were made of what you bought at the drugstore. You can do that. Those exogenous opiates, but the brain makes its own opiates, makes its own morphine, its own heroin, so to speak. And they have different names: enkephalins, endorphins, norepinephrine, and some other too. But these are the big categories. Enkephalins, endorphins, and norepinephrine. The brain's own opiates. So remember, the brain needs to make opiates. What kind of things produce it? Well, here's the list, right? Pain you got. Look at this. Exercise. So when I go to the Y and work out, I get my brain release opiates. So if I became really addicted to exercise, is that possible? Can people become addicted to exercise? Yes. This is a mechanism, as far as we know. Excitement, intense excitement, not just beyond happy. Pain, of course. Spicy food. I'm ready for my Mexican food fix. I want lots of spice. So spicy foods can induce this. Because spicy foods work through which pathway? The pain pathway. We'll discuss that in detail when we do the central system. Love and orgasm. Not just orgasm during sex, but love itself. So love causes my brain, I can be addicted to love. Duh. I can be addicted to sex. Ask Tiger Woods. Not picking on him, but he's a famous poster child of somebody that we know. So their goal is to control mood and combat pain. Close together. Like pain and mood must be intimately linked. Pain and mood. I thought pain was just a feeling. Yep, it's a feeling and it's a mood. And the link between those two is this pathway right here. So we'll come back to talk about pain per se. So you need to memorize a long list of endogenous opiates. Emotional pain, yes, we'll talk about that when we do pain. Other question? A drug you have probably not familiar with is called caffeine. I know what that is. And here's caffeine available in Starbucks. And the ingestion of caffeine makes you feel perky and alert. And the question is why? What does caffeine do? Since caffeine is the most widely abused drug in the world, you should know what caffeine does to your brain. Part of being educated, right? I should take a Twitter poll of how many folks do not drink caffeine. It'll be a small number, not zero, at least one. I myself do not drink coffee, but I never have. How does caffeine work? All right, here's what it does. Caffeine is a neuromodulator. It's a co-transmitter. It's released at the same time. When the brain drives from the gas and breaks at the same time, is a perfect example of that. Adenosine is a molecule released with the catecholamines. Catecholamines are, which ones? I forgot. Catecholamines. Dopamine was one, yes. And the next one was norepinephrine. And the third one was epinephrine. So the catecholamine, adenosine is going to be released at the same time. Gas and the brake at the same time. Adenosine is going to be the brake. Adenosine is in red, it's the brake. So do that. It's going to block the effect of adenosine, inhibits catecholamine release. So adenosine is an anti-catecholamine. So what does caffeine do? Caffeine blocks adenosine. I've lost that. So caffeine is going to block the blocker. It's going to break the brake. If I break the brake, if you have to throw the brake and I inhibit that, does the car speed up or slow down? It speeds up. Therefore, caffeine is a speed-up drug or slow-down drug. Speeds up drug. That's why caffeine keeps you awake. And adenosine, well, why is this? What is the point of adenosine? Adenosine has many roles, one of which is in the box here. When you get up in the morning, the brain starts making adenosine, and it makes it all day long. And when you build adenosine, it makes you sleepy. Well, if I'm sleepy, have some coffee, I wake up. You're familiar with this concept already. That's how this drug works. Read the box. Just think about your own use of caffeine and read that box. There's nothing else besides car accidents that increase your mortality by 50% at your age group. You're a pretty healthy group, but caffeine as well. Not just the occasional cup of coffee. More than 4 cups a day increase your chance of dying by 50%. That's a high number. So I'm not telling you don't drink coffee, but at least think about the amount that you consume. Caffeine is a drug. It is not an innocuous substance. All right. No more preaching. So questions about adenosine, caffeine? Try again. Does what contain a lot of adenosine? Nope, sleeping pills work differently. When we talk about sleep, we'll do sleeping pills in detail. Which class of neurotransmitters we were talking about do you think sleeping pills are going to affect? They speed the brain up or slow the brain down? They slow the brain down. They're going to activate calcium channels or sodium channels or chloride channels. Good job. Chloride agonists. They're like GABA drugs. They're like the benzodiazepines. They're like Valium. So your drug company, you can invent a drug that's going to act in one of these steps. I showed you kind of thing all before. We could affect drugs being born, their storage, their metabolism, degradation, their release, their reuptake. how they work in the cell membrane, many, many steps. So, have you got this down? You're like this? You're fat and happy? Yes, no? You're like this? It's one of those two categories that you're in. I hope it's the former category, but I'm afraid it's the latter category. Why don't we start here next time? Good place to start. See you Thursday.